Ladies and gentlemen, my name is Petko Zhelazov, and welcome to Ratio Online. Tonight we have a very special conversation. As you know, one of the purposes of Ratio, one of our main ideas, is to popularize science and to try to explain to the public why scientific research matters, especially when we speak about fundamental science or science related to physics. To a bigger part of the public, that kind of research seems to be an abstract because it seems like it doesn't produce anything tangible that people can really use. First of all, the purpose of this conversation that we are going to have and the talk that our guest is going to give is to show that that is absolutely not correct. Actually, a lot of things that we use in our daily lives are an immediate product of fundamental research in science and in physics in particular. And second of all, producing science for the sake of knowledge itself is also a valuable endeavor that really defines us as human beings. CERN is one of the biggest scientific projects that humanity has undertaken, and it has been, in operation for years now, and it has produced some, amazing results when it comes to our understanding of the universe and of what is it that we are made of. So we found that, having a talk with someone who represents this institution, speaking when we speak about physics, we thought of no better person than Steven Goldfarb himself. Steven has been our guest in previous shows of Ratio, so some of you might be familiar with his name and with his face, and you have probably already noticed that he's an extremely effective communicator. I had the privilege to have a few dinners with him, and he can explain like really complex topics in a way that even I can understand. Just as a general CV, Steven, he's a physicist from the University of Melbourne. He has worked on various projects within CERN, mainly in the Atlas experiment, and he has served as a MON software coordinator, an outreach coordinator, and he has contributed to early studies in the search for the Higgs boson. Steven, can you hear me?
I can hear you very well, Petko.
Steven, welcome to the show.
Thank you so much. It's such a pleasure to be back with Ratio, to be back with, as we're all in our homes,
Right.
but to be working back with you, Nicola Dimitar, everybody on the Ratio team. I always enjoy it, and I especially enjoy being with the Bulgarian crowd. They're fantastic. We'll see. We'll see. All right,
Yeah, one of the great things that we do is because during the course of the preparation of the talks that we had, the live talks, previously, we get to spend a few days together, pre-event and post-event. So it's really nice because we can really develop a relationship. So it's not going to be an overstatement if I say that I miss you, mate. It's been a while, so it's really nice to see you as well.
I miss you too, and I miss those interactions. Those were the days. Those were the days we used to get together, and I love Sophia. I'm gonna miss my favorite bartender Plamen over at the Petal. I'm not gonna get to see him this time. I'm gonna get over there sometime though.
All right.
But let me get on with the show, as we all do with
Yes,
Zoom.
go ahead. So as far as I understand, you're gonna give us a short presentation, not a short one, but we'll spend a good part, half of the show, of you giving us a talk, and then we're gonna spend some time for a discussion. Just for our viewers, again, you can see here below, you can submit your questions. It's sli.do with a hashtag CERN. So listen carefully what Steven has to say, and you can submit your questions, and then I'm gonna put them forward to him. So Steven, you have the floor. If you're ready, you can go ahead and start.
I'm ready. So are you guys seeing my screen now?
Yes, sir.
Just to make sure. Okay. Yeah, I mean, you set the bar pretty high too. Thanks a lot, Petko. I can answer all your questions and you'll understand. I'll do the best I can. But I love good questions because I love what I'm doing. So let me tell you a little bit about it. And I also love your graphic designer for making this this first slide. I think it's fantastic. We'll give her a shout out later on. She did some other work for me here. So let me get started here. So first, it's like the publicity. I don't know if you go to any podcast, they always start out with their publicity first. I want to advertise this place called Bulgaria. I just want to say a few things because I think it's rather important. Many people might not realize this. First of all, Bulgaria is heavily involved in research, particle physics research. They are, I think they were the 20th member of CERN, and that's something to be a member of CERN. It's a high bar to be able to attain that. And they're very active. They have a lot of physicists on the CMS experiment, which is on the Large Hadron Collider, very successful experiment. They've had over 1,000 papers come out from there, and I'll talk to you about that. They're also members of IPOG, which is dear to my heart because I'm chairing it at the moment. That's the International Particle Physics Outreach Group. What that means is that if you are listening in and you're a teacher or a student and you would like to learn what it's like to be a physicist for a day, you just have to contact your IPOG representative. You can find me and I will point you to them, and they will tell you how you can have master classes, either at home or in your classroom, depending on what COVID lets us do. Okay. Finally, a big shout out to these guys. I don't know if you've ever heard of them. It's a team called Ratio. I think they're fantastic. I love working with them. I had the honor to be on Ratio in 2017 to present, and they got 800 people together on a Sunday morning at 9 o'clock, which made me very happy. But they also helped me out with some other things I organized in Sofia in conjunction with the conference there, and it's always a pleasure. And so I give them a big shout out. Watch all of their shows. They're great. I'll start out with this. Now, if you've seen my previous talks, I always start out with this sort of disclaimer. This talk's going to contain actual facts. It might not be convenient for audience who prefer alternative facts or outright follow your own risk. This, just to remind you, this used to be funny. It's unfortunately, after 3 years, it's become a little bit more tragic. And so I want to talk to you a little bit about that because times have changed, as we all know, for many, many different reasons. There's some things that we don't see much of these days. I don't know if you guys remember this. Try to think way back, the Wayback Machine. We used to actually touch each other when we came to meet each other. We would shake hands. Even in France, of course, we would kiss each other. That's a normal thing to do. That's our president there. And students would go to classrooms to learn. They would all work together, and we all loved that as parents. We would go to bars, restaurants together. We would go to concerts and get sweaty all over each other and have a great time. There was also other things that changed during this time. I mean, do you remember there were these things called glaciers, ice? They were like, on the poles. I don't know if you remember that. They were really cool things. Really cool. They kept their planet cool. And there were also forests that weren't on fire. So these are just things from the past that we miss, right? There's also things that we see too much of these days. I love the look of this. The guy doing the interview's face is just priceless. Just to remind you, if a psychopath is talking to you, don't listen to them. It's not healthy. This was lie number 20,001. Actually, I'm making that up. Is more than 20,000 lies have been said by this person on your left there since taking office in the U.S. More than, and that's a count by the Washington Post. What I miss the most out of all of this is this thing. Maybe you can remember this thing called truth, where people said things which were based on fact, things that they'd measured, evidence. This came out only a few months after Donald Trump had been inaugurated in the U.S. Times, a U.S. magazine, but I think it's read the world around. This made me very sad to see something like this, but already there've been enough lies being said. When one person says them, they go everywhere, right? It suddenly becomes okay to say them. But I'm still an optimist, and I don't believe it's the case. The truth is dead. And the reason why I would say so is this. This is the view actually I'm looking at right now. If I turn this around, you would see this outside my home. I'm very, very fortunate living in an area called the Pays de Gex, which is near Geneva, Switzerland, on the French side of the border. It's the Alps over there. The clouds are slightly different today, but not much different. And what you can see here from this view is actually this place called CERN. That's where I go to work. And it's a fantastic place. And if you look very closely, I claim it's a truth factory, and I can tell you why. I zoom in on it, and if you look carefully, you'll see this. Huge numbers of publications coming out of that place from just the Large Hadron Collider. And that's not the only game in town. There's other experiments at CERN, very active experiments in many different areas of physics. But just from the LHC, there's more than 3,000 publications have come out from the experiments there. That's really impressive. You say, okay, it's just they wrote a lot of papers, right? That's all. You know, they've been operating for a while. Well, let me just to give you an idea of what it takes. Okay, first of all, let me show you the score, just so you know what the score is right now. What we see here is lies 20,000 and truth 3,000. But I don't think it's the quantity that's important. I want to talk to you about the quality of what's behind this. What's the difference? This is what it takes to write a scientific paper. This is simplified, greatly simplified. There are loops in here. There's sometimes things that drop out. And I want to take you through this because I think it's very important. First thing that happens, a theorist will tell you it's just have an idea. I say no. I would say as an experimentalist, as any scientist, you notice a phenomena in nature, some pattern. You notice something. The sky is blue. It was blue yesterday. It's blue again today. You sort of see a pattern, and you have an idea on that, something you want to measure, something you want to verify. You read literature to see if someone else has already done the research. If they're not on your experiment, that's okay. If it's on a different experiment, you might still want to do the research. You talk about it with your friends. You have a lot of coffee. Coffee is critical to the scientific process, any scientific process. By the way, this applies to all the sciences, this method here. You talk about it and you refine your idea a little bit, and then you propose it to your team. Typically for us, we have many physicists coming from many different institutes. You talk about it with usually your institute's team first. They give you some ideas, you refine. You might try some simple simulation, check the validity of your methods is something that can be done. Then you refine the proposal and you come back to what I call a subgroup. It's not, all the structures aren't the same in all the experiments and all the sciences, but typically here we might have a Higgs group, and then underneath that you might have like a Higgs subgroup, like the Higgs to BB or something like that. It's the way things work. So you have a subgroup and you'll present it to them. They'll say, yeah, this is good, or maybe it's, we already did that, doesn't work, blah, blah, blah. You'll refine it. If they say they give you the go-ahead, they give you some simulation time, some computing time. You'll do the simulation, and then you're going to sort of look at what are the backgrounds, what's the signal, and you'll try to get an idea if you can do this or not. Then you're going to try to develop a method to extract the signal from the background. That's the really tricky thing. Try to pull it out from there. If you see that you can do it, then other thing you're going to start studying, and you study this all the way through this process, is something called the systematic uncertainty. This is really important. Many people don't get this about science. We don't just give you a number at the end of the day. We don't give you an answer. We say we know this answer plus or minus something. The answer is 3 plus or minus 0.01. We try, and we spend a lot of time, in some cases years, working on this. The measurement might come out almost automatically. It might be a simple calculation. It could be one line of a code to calculate the mass of a couple particles. But working on understanding how well you know that is where we spend an enormous amount of time. Okay, so just so you know that. I want to hammer that home because that's important to me. You'll present this to your group. You'll get criticized. We always get criticized. You'll refine your method. You'll apply it. Finally, when it's time, you apply it to real data, and you'll compare it to the simulation. You might see something strange. Usually you'll see something strange, and you'll doubt your results. And emphasize that point too. You will doubt yourself. Did I do this right? What mistake did I make here to see that? And you'll keep trying, and you'll do different methods until finally this thing stays, and you say, okay, maybe it's true. And then you'll go to your group, you'll get criticized, you might refine some things, et cetera, et cetera, et cetera. You'll write it up finally, present it to the group. They'll give you some changes to make. And finally, you get to a point where you can present that to a publication committee, and they help you to refine it. And then when you're done with that, then you're going to go, and the whole collaboration. In my case, there's 3,000 authors out there. They will get a chance to criticize it and to give you some changes that you need to make. When this is all done, then you submit it for publication, and once more, you're going to go through this hurdle of having others from different experiments, your peers, review it. And then you publish or not your paper. This is what you have to go through to publish a paper. This is the cost of truth. Okay, if you really want to be able to say something is the case, it's true. On the other hand, and the other 20,000 looks something like this. You get a half-assed idea, or you're just angry, it's the middle of the night, have a cheeseburger, you punch some random words in your phone with your greasy thumbs, and if you're a professional at social media, you'll add an image there, or if you're under 30 years old, you'll add an image to it, and then you'll hit tweet. So this gives you an idea of why you can, if you have a very loud platform, one where everybody sees things, you can just outnumber the truth with garbage. But you guys now know better. You know what goes into garbage and what goes into truth. So let me tell you a little bit about what's in the paper. Let's get to the substance. I've told you the process, what's in the substance. So I have to go back to some of the first planning, and some of you who saw my slides before might have seen this. I just like this one. That's all. This is from one of our very early planning sessions for a study, pre-LHC times. This is Og, and she's talking to her subgroup here about some ideas that she had, and it was based on some of the work of her student Zog. And Zog had done some ideas. He said you smash things together and you can try to figure out what's going on. It was groundbreaking research at the time, and they decided, well, this is worth pursuing. Okay, let's pursue that. They wrote down, chiseled down their ideas. They said, okay, what do we want to figure out? What do we want to know? And what they want to know is, where do we come from? What are we made out of? Where are we going to? What are the rules behind all of this? And is there anything else that we're missing that we don't see? Scientific goals. So chiseled those down. Say, okay, now we got to build an apparatus. Okay, we got to try to answer these questions. The instrument they thought of, they said, well, it'd be nice if it had electromagnetic sensitivity. You can see light, different wavelengths of light, precision spatial resolution, a high zooming ratio, some fast readout, and we want a multi-core neural network processor. So the device they came out with was here. You can see it here. It's an amazing device. It allows you to do incredible amounts of measurement. It allowed us to do measurements for hundreds of thousands of years and precision measurements. If you don't think it's precise, take a look at this. This is my friend Eva. I think she's listening in, by the way. Hi, Eva. This is her hair. She has lovely hair. Eva is from a place called Bulgaria, and where the women have beautiful hair, I should tell you. And you can see here, if she allows you to get within 15 centimeters, I was very lucky on this day. I snuck up and got the picture. There you can see 10 micron precision there. Thickness of a hair is very, very thin. I'm sorry, Petco, you probably don't know about this, but the precision, the precision of that hair is about 10 micron precision. You can also look very far out into the distance. So if you're looking out into the distance, we can see the next closest galaxy, one that we're actually going to collide in, Andromeda. You can see it there with your bare eye. All you need is your eye, and you can see that. Don't worry about the collision. It's not going to happen during this talk anyhow. It's going to take some time. Since that time, there were upgrades between the proposal and now. I'm just going to take you through history very, very quickly. For looking out into space, this guy Galileo had some nice ideas, used optics, and you could see moons around Jupiter, which actually you can do this yourself too. These nights, you can see these moons around Jupiter. You can, we decided, hey, let's get outside the atmosphere. So we invented these devices, which we can shoot up into space and get beyond the atmosphere and do precision measurements and look all around us to see what's out there in space. And we also built these incredible devices, which can listen to what's going on in space. This device here is called LIGO. And it's just a brilliant idea. Light is shot down these two 90-degree posts, and it goes through a mirror, and it's set up to such a precision that they can measure any changes in length. Like if the length of one of these legs there were to change by a fraction of an atom, they would see it. And that's what's necessary to be able to measure if space-time itself is rippling. And space-time itself would ripple as predicted by Albert Einstein. He was a guy pretty bright from around here. If some enormous gravitational events were happening back in time. So as an example here, the first one that they really saw was the collision of a couple of black holes, enormous black holes. They collided, and that caused ripples in space-time, and they were able to see the change in size and dimension of these legs. Beautiful experiment. Nobel Prize was given out for this. Obviously, it didn't take very long to get that out. I highly recommend that Ratio, if you haven't done it already, get somebody who can talk about LIGO. There's also the Virgo experiment in Italy. So let me talk about looking in. To look in, this is the stuff I like to do. Here's Eva's hair again. If you look close at it through a microscope, we started to make these microscopes so we can see a little bit better. This is not on Eva's hair. I can vouch for that. This is an ant who also has hair. But we just found out that you don't just need to use photons. If you use particles with a mass, you can actually go to higher precision. It turns out that the higher energy you can go to, the shorter the wavelength. You guys all know that. E equals h nu. You all learned that in physics class. The wavelength gets smaller. That's why we need enormous accelerators, is to go to smaller and smaller distances and to probe and to get precise measurements. So we did this with electron microscopes. We upgraded, we continued to build devices to go to smaller and smaller wavelengths. We built these accelerators. Here you can see a bubble chamber, which is not so long ago, it's a few decades ago, but I mean, it was a wonderful device. You could see particles, charged particles curling in a magnetic field, and you could thus measure what their energy was. And then you could figure out, the particle, and we made lots of discoveries this way. I think this is actually the discovery of the positron, what's in this image, but it doesn't matter. They were beautiful, beautiful images, inspired, by the way, by beer. Beer, when it bubbles, is due to something exciting part of it. It's just a prop, okay, so now what are the results? What are some of the things we learned from all this? I've said this to you guys before. I'm going to tell you again because some of you are different. It looks like, yeah, some of you are different. This is, we live on a beautiful blue marble called Earth, an incredible planet. We were very lucky. Well, it's the reason why we're alive is because we have this thing here. There isn't another one nearby. There isn't a planet 2.0. We got to save this thing. It's beautiful. And it's in a solar system at just the right distance from sun. The sun is a star. It's one of 100 billion stars in our galaxy. And that galaxy is one of 100 billion galaxies in the universe. These are plus or minus. I'm a physicist. If it's 10 billion, if it's 100 billion, if it's a trillion, doesn't matter. But it's a lot. Okay, a lot. We are very insignificant. That's an important thing to remember. It's a nice thing to remember. It frees us up a bit. We also learn not just about the spatial dimensions, but we learn about time, because you can see from the wavelengths of light coming from stars, from galaxies and clusters of galaxies, you can figure out if it's shifted in a certain direction or another. You can figure out if things are moving away or coming closer to you. Red shift means it's moving away, blue shift it's coming towards you. And from that, we can figure out the information about the beginning of time. We see light that's taken a long time to get to us coming from the very beginning of time, 13 billion years ago. So 13.8 billion years ago, we know, was around the beginning of everything, the beginning of our universe. Space-time started then. It expanded rapidly. Then it did this long expansion. And now the expansion is accelerating. That's a strange thing. Okay, I'll talk a little bit more about that later, but we're getting bigger and bigger, faster and faster. My wife says that about me as well. So happens. We also learned, looking in, we learned, again, looking at Eva's hair, we learned that there's cells in there. As we got closer, we found out those cells are made out of molecules. Molecules are made out of atoms, which we were sure was it. That's why we called it atom. But then we found out that atoms have a core to it. They have a nucleus. Inside the nucleus, there's protons and neutrons, and there's electron cloud, probability cloud around it. So we learned all that. We learned that these protons and neutrons are made up of things called quarks. And this has been some more than 50 years or so since we started really understanding all this. But since that time, we've mapped it all out. We've made our sort of table of elements of the fundamental particles. Let me just stress that, fundamental particles. That means they are not made up of anything as far as we can tell. They are it. They're the Lego pieces that the universe is built out of, okay? They have no volume to speak of. They have no structure to them. They're just point particles, and they're out there. And these are you can see the red ones here are called quarks. We give them fun names because why not? It's all we can do as scientists, come up with some fun. We have quarks. We have leptons are underneath it. The orange ones are the ones that the sort of substantive. The I don't know how to describe this, but the green ones are called neutrinos. They go through everything. They hardly interact, whereas the electrons, muons, and taus interact electromagnetically. That's the difference between them. And the particles on the right in blue, those are called bosons. They are the force-carrying particles. They will propagate between the other particles to cause the interactions between the particles. They cause the interactions. And so you see these Legos we have to choose from. And then on the right here, the coffee cup gives you the rules. We managed to put all of the rules you need to understand how those things interact onto a coffee cup. That's pretty good. It makes you pretty happy that you can. I should have that coffee cup. I have a different one today, but it's all right there. There it is, all the possible interactions. And along the way, I was just asked to present this. Some things happen along the way. You know, when we're doing fundamental research, accidents happen. You come up with ways to do, you know, large-scale agriculture or industry. You might figure out how to create, you know, power in efficient manners. You also, you know, getting closer to particle physics, come up with tools for medical imaging like PET scans or MRIs, or even methods which are relatively recent for shooting beams, hadron therapy to cure what you find with the medical imaging. These things come out because we're pushing our technology to its limits, and we're pushing our methods to its limits, we're pushing our minds to its limits. All of those things are necessary to be able to do these things. And then finally, a couple things which I don't know if they're ever going to make it. Touch screens, who's going to use that? World Wide Web, I don't know. You know, maybe it remains to be seen if those things become useful or not. These were things which CERN actually itself, that place just out there, helped to deliver to the world. But you know, that was an accident. We're interested in the research, right? Our most recent upgrade that we did along the way from Og and Zog's technical report went a little bit further, and this is something called the Large Hadron Collider. And this was built, now it's been a few decades ago that we started building. That took quite some effort. We finally really came online for good in 2010. So it's been 10 years since we've really been operating. It's actually not that long when you think of everything that's come out. This was before it was turned on even. You can see it's still all, you know, got the wrapping paper on it. It looks like this on the outside. So this is from up above. You get the idea. You cannot actually see this when you're up above. You don't see all these lines. We use several of the older accelerators to get the protons. We use protons in the LHC to get them up to speed, to get them up to energy. We accelerate in one, we go to another, we accelerate, we divide them up, make the beams the way we want them, shoot them into the LHC, and then accelerate them up to the energy that we need to do our work. The highest energy actually that we can possibly do in such a small 27-kilometer circle. You know, the main reason for that, you know, you guys all watch car racing. You know, if you have the bigger the track, the faster you can go. You know, you lose energy when you have to curve. That's all you really need to know about that. We use magnetic fields to curve charged particles, and you have to be big to get to high energy. You need high energy, as you guys already know, to look for things which are very, very small. So this is the motivation behind this. There's actually another way to look at it. Particles which disappeared at the very early universe that are difficult to see now because they disappear quickly, they transform, are the more massive ones. More massive particles transform instantly to less massive particles. We're made of the least massive particles. We are made out, if you have an up quark, a down quark, electron, you can make us. That's all you need. Those are the least massive particles. They're stable. All the other ones in our table are less stable because they're more massive. And the more massive are, the more different ways you have that you can transform to the other particles. In order for us to produce those more massive particles, we add energy to the lighter ones, and then we can take that energy, and it can form into E, make mc squared. Okay, so that's the other way to look at it. All right, we'll have a quiz at the end of this. This is what's at those 4 different places there where we collide. These are the 4 places in the LHC where we actually pass the beams through each other. Don't worry about it. Ghostbusters said that wasn't a good idea. It is a good idea. We pass proton beams through each other. Now, to get an idea, this is not an easy thing to do. We have, in fact, hundreds of billions, just like the galaxies. We're trying to do the same. You know, if you took, by the way, just so you know, this is an interesting fact. I shouldn't digress because they gave me a certain amount of time, but I got to digress. I just do that. If Andromeda and the Milky Way are going to go collide, right, 2 billion years, and when Petco is getting old, they're going to go through each other, and the number of stars they're going to hit is actually been calculated to be 0. So even though you have these very dense galaxies, they're going to go right through each other. And the same thing happens here. Unless we squeeze these beams of protons as tight as possible, and we do that, and we get billions and billions, 100 billion against 100 billion. When we do that, we get 50 or 60, which actually collide. It's a very, very difficult thing. Mother Nature on the inside, it's just like Mother Nature on the outside. It's full of nothing. There's a lot of nothing out there. But we do that. We make them collide at these different detectors. I work on the Atlas. Atlas and CMS, those are sort of general purpose detectors. And there's the other ones, LHCb and ALICE, and I'll tell you a little bit about them as we go through. Beautiful. They're all incredible devices. Some of the questions that we've answered. This was a very fundamental question that we had going into the process, and we had an idea that we might be able to find a solution. How do fundamental particles, I already told you they were point particles. I'll never forget the TEDx I gave where I called them pointless particles. You know, things come out of your mouth. They're point particles. And they have a mass. They have different masses, and we were clueless. So in 1964, some very bright theorists, here you see Peter Higgs, who was also Francois Englert, Robert Brute, they all looked into these and tried to figure out how is it that a fundamental particle gets a mass? Why does it have a mass? It doesn't make sense. Our mass is mainly made up of, you know, dinner, lunch. It's chemical energy. It's chemical binding of molecules, or even within atoms, there's binding energy. That's what's most of our mass. A tiny bit of it, though, is this mass, is the mass of the fundamental particles. And they get it because they interact with the field. They came up with this idea. It's very similar to electromagnetism. A charge going through electromagnetic field is affected by it, and because of the amount of charge it has. So a measure of how much it interacts is charge. It's a very similar thing. So a mass of a particle is how much it interacts with what's now commonly called the Higgs field, or you can use it by all of the names of the physicists. But that field, they proposed it. But they said, you guys are never going to find it because it's going to be too hard, because things interact with it so weakly that it's impossible. So we went and found it. It took us 48 years from start to finding it. It was not easy. We had to build stronger and stronger devices. It took us getting enough energy density to be able to, you know, think of the field like a very clear pool of water that you just don't see. It's so clear, there's no reflection. But if you drop a pebble in it, you'll see the splash. That's essentially what happens here. These are the splashes. We made those splashes. We built by colliding the protons. Actually, it's the gluons inside the protons. I don't want to go into details, but they interacted with each other. They formed for an instant a Higgs boson, which then decayed. We don't find it picture by picture, but it's nicer to see the pictures. We find it statistically, but there you can see some nice images from the Atlas and CMS experiments. So that discovery was in 2012. Since then, we've measured the heck out of it. We're still measuring the heck out of it. That's what we do. It's once we find something, we measure it and measure it and measure it. And we still want to do much, much more than this. I love this plot. This plot is so beautiful to me. That line goes straight through the data points. And that's just so cool. We have found that, yes, indeed, the mass of the particle tells you how much it's going to interact with the Higgs field. As its mass goes up, its interaction with the Higgs field goes up. And so we've nailed it. We're going to keep measuring it. We have other particles, the lighter particles, to look at to make sure that's the case. We would love to find something that disagreed, because that's how you go forward in science. You find something that disagrees, but that's where we're at right now. Pretty damn good. Some of the other LHC experiment discoveries, I'll go very quickly. We've seen the world before protons were born. The quark gluon plasma is sort of a primordial soup before they got together, the quarks and gluons, to form protons and neutrons. This is from the ALICE experiment. This is their expertise. They really look at and measure this. Other experiments, ALICE and CMS, also measure this, but really ALICE, that's their thing. And they bring some very beautiful measurements on that. Quarks don't just get together in pairs and in triplets, as we'd measured before. We knew it was possible for them to get together in 4s and 5s, but we hadn't really seen it and measured it, and now that's been done. LHCb has made some fantastic measurements of that. Tetraquarks and pentaquarks, they call them. Really, really nice work. This is, I love this image too. This was something Atlas did. It was a really brilliant idea for our lead, the people who look at lead collisions. Sometimes instead of colliding protons, we take lead, take off all the electrons, easy, take them out, and we have them pass through each other. And that's how Alice did the images you saw from the Alice experiment. Someone had the idea, well, these things have tons of photons traveling around with them. They're highly charged. Let's pass them through close to each other so that only the photons pass through each other. And if there's enough photons, there's this really low probability that they will collide. But if you have enough of them, you'll make it happen. And we saw that. So if these are photons colliding, you see nothing, and then you see 2 photons come out. That's just really, really beautiful. I love looking at that. We also recently published something. I'm sorry if I'm a little bit biased towards Atlas. I work on Atlas, but and CMS and the others have done really good work as well. This was a really nice result recently where we keep testing this idea that the different leptons, electrons, muons, and taus are the 3 different types of leptons, that they interact in a similar manner. And you can see that line, the data measurement within less than a sigma is really close to 1. That's what you would expect. The ratio of how something interacts, W's interact with taus and with muons. And we measure it, we test this all the time. We're doing tons and tons of tests. Finally, let's see, I can just tell you this, we've also measured other things in really, really sharp precision, because by measuring things in precision, like the W mass here, you can look for slight differences. And what we really want are slight differences with our model. So you can see these very nice ones. Also the nice CMS measurement of top, it's a top quark there decaying to B quarks. And then I'll show you this very quickly. And we're not going to go over this in detail. Don't worry. It's just to show you, we do lots and lots of searches. So this is exotic results from CMS. Excuse me. These are all a whole variety of searches they just presented in our last major conference. All these searches are these are maps. Look at this as maps. There's no El Dorado in here, but there's a lot of maps. We've covered lots and lots and lots of ground. And that's really important. That's what we do as physicists. There's still questions that are unanswered, and they'll look familiar to you. They're Og's questions. Where do we come from and where are we going? This is a big question. You know, and it's also most of our universe. What is causing this expansion? What's going on here? Where are we going to go? Are we going to expand out until we have a cold, dark universe that just disappears? One would expect the mass of all the things out there to pull us back together at some point, that we wouldn't accelerate our expansion. Yet we're seeing that. What is it? We call it dark energy because we're stupid and we don't know what else to call it. We don't know what it is. That's all. I know that our great-great-grandchildren will laugh at that we call it dark energy when they figure out what it is. But that's what it is for now. We call it dark energy that's pulling it apart. Why do we exist? From all we can measure at the very beginning of time, 13.8 billion years ago, when Petco was just a kid, the universe came into being, and there was equal amounts of matter and antimatter. We see these symmetries in nature: matter, antimatter. We have electrons and we have positrons. We've measured this. When we see our collisions, we produce equal amounts of matter and antimatter most of the time. So at the early universe, when we had matter and antimatter, it all collided, actually came together, and made energy, just like, Tom Hanks showed us in can happen if you bring matter and antimatter together over the Vatican. Well, I'm not going to that, but it really does make an explosion and gives you a lot of energy, and that's what happened. And all the matter and antimatter disappeared, except there's a little bit of dust that remained, and that's us, and we don't get it. Why? Why did something? There's some imbalance there we don't get. There's still always this question, even though I have just told you that quarks are it, leptons are it, this is it, these are the fundamental particles. We're still going to keep checking to see if they aren't made up of something else. Why, for example, are there 3 families? Maybe that's because there's some structure underlying it. We don't know. Who knows? We don't know. So we just keep measuring. It's one of the things we always will measure. Why is gravity so weak? I know that gravity doesn't always feel weak. When you woke up this morning, it didn't feel weak. It kept you down in your bed, but it is weak. It's incredibly weak compared to the other forces, and we just don't get it. If you look at the numbers I have there, the strong nuclear force is 60 times the electromagnetism. Okay, weak nuclear force is about 1/10,000th of the strength of electromagnetism. I mean, this is at a certain. It depends on what energy you're at. But there's just not a huge difference there. For us, for a physicist, a few thousand is nothing. Gravity is a million times weaker than the other forces, and we just don't get it. There's a variety of proposals out there. Maybe there are extra dimensions, and gravity hangs out in the other dimensions, and we don't see it in ours. We only see a residual part of it. We don't know. We don't know. So we look for these things. Theorists come up with ideas, and we try to check to see if they're there. Finally, I should mention this, because this is something which I really, deep in my heart, think the LHC has a chance at solving. If not the LHC, there's other really sensitive experiments going on, and that's this. This woman here was a brilliant astronomer, not given the Nobel Prize, who should have been given the Nobel Prize. I don't know if I'm making an opinion clear here. She got these nice device that allowed her to measure the speed of stars and galaxies, and she clearly expected to see that gravity would act like it does in the solar system, for example, that you would see the stars closer, moving at a faster pace than the stars on the outside. You can calculate all this as Newtonian physics, and it wasn't close at all. In fact, the stars on the outside spin around nearly as fast as the stars on the inside. And she proposed that to explain this, it must be that there's something else in there, something we don't see. And it was referred to by another guy named Zwicky before her, that there was something out there called dark matter. And so she labeled it dark matter, and we still call it dark matter. So this is some substance that's out there, and we can see its effects. We can see it lensing the light from stars. We don't know what it is. So just sort of sum up, just as we all thought, the universe is a beer. Something like 95% of that beer is stuff we never see, that we don't understand. 68% is this dark energy. 27% is the dark matter. Actually, 4.5% of the stuff that we do see is just interstellar gas. We're like 0.5%. Okay, I mentioned we're insignificant before. We're still insignificant, which is great. That's not a problem. Don't worry about being insignificant. I think it's a good thing. I mean, there's much more out there for us to learn. So what's next? We've done a lot of good work. There's much more to do. And we just had a meeting. It's called the European Particle Physics Strategy Update. There's also meetings going on in other parts of the world where they're looking at what should we do. Every once in a while we have a rethink. I think it's like every 7 years or so we think, what are the next steps? There's new technologies. We found new things in physics. What would be the next proper steps to take to use? We know we're very well conscious that the fact that we're using the world's resources to do this. It's not a huge amount of resources relative to what we spend on war and other things, but still, it's our resources. This is tax money that we use. So we think very carefully. We take our top physicists, we make them think about this. The theorists come up with the different possible theories, different scenarios of what we could determine. And we spend, for this, just to come up with a time, I'm not going to go into detail on this, but 3 years of planning, essentially. Everybody gets a chance to give input to this, and we come up with what's the best possible plan for the coming 7 years. You can see here that they plotted out, I mean, it's 7 years. In fact, here they plotted out 70 years. Okay, not in detail. It's the closest year as you plan in detail, but we have a rough idea of what we want to do. And it's on a slide that was in Comic Sans, which I think is dear to my heart because our Higgs discovery was in Comic Sans. But you can see here just a long-term plan. We have some really, really good ideas put forward, not just by CERN, China, Japan. These are for high energy. The US is also deeply involved. They'll be involved on these experiments, and they're looking at things in neutrinos in the US a bit more than this, but we're all involved in this planning here. And so we have a plan. This is 70 years of physics. So when the media get a hold of this, and when they get a hold of the different ideas, they're going to put a price tag on it. Please keep in mind, it will be an expensive price tag, but that price tag is for 70 years of research, thousands and thousands of papers, thousands of students, of the training of thousands of students. And so it really is a lot of big bang for the buck, I would say. This is just some basic ideas that are thrown out there. Higgs factories, I mentioned that once you find something, you want to measure the heck out of it. That's what we do. That's what a Higgs factory will do. It will collide electrons and positrons. There's different ideas, perhaps a linear collider at CERN, perhaps a linear collider in Japan. Japan's pretty keen on that. And also in the longer term, we're considering building a very, very large ring that will dwarf the LHC around here. And our first step will be to put electrons against positrons there, and then to go up to colliding protons. So you can see the same picture, sort of, if you look in the upper right, same picture, but it would have protons instead. So the other areas we collide hadrons. The first one you see on the left there is the high energy LHCs, possible plan where you go up to higher energy than we're at now. You know, that depends on the kind of technology we can get with magnets. So there's different ideas out there. And also China's really keen on getting involved. It's a hard game. They are involved. They have physicists involved. I think we should embrace them really and help them to get going and to be a part of it. I think the real difficulty will be international collaboration. All of these require international collaboration. It involves an openness that we're used to, sharing of everything. So I hope this would help. We would embrace them if they can go in the right direction on that. Just to sort of finish up here, I just want to say all of these plans, I'll be happy to talk about them in our discussion session. They all are long-term sustainable projects. They will all drive technology. They're things that I know that we are in our mind, we're thinking, you want more money, you know, our economies are collapsing. Well, these are the things that get your economies going and going in the right direction. It creates international collaboration. But they have one key goal, which I want you to remember, and that's this. And I love this. Thank you, Dana. It's a shout out to Dana. she made this gift for me. That's our basic goal there. We want to outweigh the lies that we're being pounded with truth, with data, with evidence. We want to make decisions based on evidence. That's, excuse me, that's how we'll go forward. Excuse me. So just to summarize, so it's a pursuit of the truth. That's all I'm advocating here. We need to pursue the truth, doing fundamental research. It's not just particle physics. Fundamental research is how we get to the truth, what our universe is about, and sharing it. Just a very quick picture here to sort of summarize why. You may ask, why is truth so important? Well, over time, we've evolved, and we've evolved from a simple creature to something relatively complex, something able to come up with the idea of the Higgs boson, for example, to pursue it and to discover it. I mean, it is an amazing thing that humanity has been able to get together and work out that problem and solve it. So we've evolved. Now, it's not true in all cases. There are some chains of evolution that unfortunately didn't follow that path. And I feel you can feel sorry for them. But over time, we will go in the right direction. I'm confident of that as long as we keep pursuing truth. Okay, that's what will end chains like this. The evolution of human beings, if you look at it, and there's a very nice talk given in the concluding remarks during ICHEP, our last conference, which I really liked a lot. Our species, Homo sapiens, we weren't necessarily the strongest, There were other species that perhaps were stronger than us. It wasn't necessarily this evolution didn't necessarily happen through picking the strongest. Strength helped. Speed also helped, but it wasn't necessarily the criteria that was most important for our evolution. Intelligence helped, having a bigger brain size. But there's evidence now that perhaps we're not the ones with the biggest brain size of all the different species that were our ancestors. We don't always use it well, but intelligence wasn't it. What really was key was this: empathy. Empathy was very important. Empathy was what taught us that there are other human beings out there. They're the same species. They have similar feelings to us. They have similar needs. We need to work with them. We need to cooperate with them. Cooperation is everything. And if you're going to cooperate, then you need the truth. You need honesty and the truth. So see these guys, bye-bye. Those guys disappear when I talk about that. We need to cooperate. Honesty is essential. We need to trust each other to cooperate. That means we tell the truth to each other. So if there's one thing I want you to get from all of this is this statement. I want you all to say it out loud. I won't hear you, but say it out loud now. Truth is a thing. It exists. Thank you.
Thank you very much, Stephen. That was not only very informative and fun, but inspirational as well. Also, well done, mate. That was good. That was good. Now, before we move to the specific physics questions that we have prepared and that people are currently submitting, I'm going to ask you to solve the world really quick.
Okay.
As a physicist. So you did mention something there. This GIF that Dana created for you. The tweets against the facts. Now, have you got any quick low-hanging fruit idea of how we can translate the accumulation of scientific fact and truth into public policy? Go. You have 2 minutes.
It's the method. The method. Follow the facts. Mm-hmm. Do the hard work. It's hard work to get the truth out there, to find out what is the truth. If you follow social media, fine, but find somebody who's doing fact checking. Look for truth. Look for truth wherever you can. It takes more work than just reading the tweets that are popping out. Make sure, get out of your bubble, look at what the other people are saying, and then check fact checkers to make sure, that there's some truth. You have to do the research. I'm not saying you have to believe scientists. Forget what I say. It's not important. You have to believe scientists. You have to believe science and believe the method of how we go about getting the truth. That's what's key, that methodology of seeking the truth.
Right. This is what we are aiming for as well, by telling nice stories and by having people like you, not only for people to understand fact, but to get the essence of the scientific method itself and to apply it in life. Before we continue, really quick, Stephen, I'm going to ask you to stop sharing the presentation so people can see my pretty face as well.
Oh yeah, we want to see that.
I'm currently sparkling for some odd reason. So yeah, there we go. Very good. All right. So, okay, let's move to the physics now. Now, first I want to ask you, because you did show that within Sun, you have, a few different experiments, you have several detectors to measure, pretty much the same thing. Why do you have that?
It's pretty much for the similar reason that we have so many different physicists. You have different points of view, different methods of doing things, different manners of measuring. So the experiments were all built by different groups with different ideas. The technologies are very different. If you look at the Atlas and CMS experiments, those two, which are the general purpose experiments on there, they'll look very, very different. Atlas is larger in volume because it uses a different kind of magnet system on the outside. It's called a toroidal system, which meant, was to optimize our measurement of muons, of high energy muons. Whereas, CMS is denser. It weighs twice as much actually as Atlas. And it has really a very strong magnetic field for tracking on the inside. So we're somewhat complementary on the things that we measure, but we both, really wanted things like the Higgs boson. So we both did the best we could to find a way to measure that. And then we could check, just recently, there were some nice measurements. Both Atlas and CMS have started to see the Higgs boson decaying to 2 muons. We're not allowed to get excited because it's not 5 sigma. So we're not allowed to jump up and down and drink beer and all of that yet. But we both see little bumps in the same area. And that gives you a lot of confidence. I remember the Christmas before 2012 when we found the Higgs boson, we had that same sort of excitement. We'd seen little bumps in the exact same area and using different methods. And then we knew it sort of confirmed that, yeah, there's something's going on there. We're going to find the Higgs. So it's very important that you can check each other. We do something what I'd like to call co-opetition, and that we compete with each other. We don't want to see each other's work when it's going on. And we go basically from conference to conference. There's a conference coming up. We don't look at each other's work. We do our own thing. That's very important to stay independent. If they see a bump somewhere, we don't want to form it by looking for it at that specific area. Okay? We want to stay blind to anything they're seeing, and vice versa. And so they do their research, we do our research, then we present it to each other. And we both, of course, we're competing. We want to show a better result than they have. Right. And that's a fun part of it. But then right afterwards, we're having coffee and we're talking about it. And what kind of method you use? And we discuss this. And then we use those methods and later on. And so there's that and even sometimes we put our data together so we can get an even more precise measurement. So it's very, very necessary that we have several experiments. The other ones, LHCb and ALICE, for example, on the LHC, are focusing on different problems. LHCb, which found the tetraquarks and pentaquarks, they're actually really focused on this antimatter problem. They're studying specifically B quark decays because we have seen a process in there that's called CP violation. You don't have to worry, that won't be on the quiz, but it means that they can decay a little bit more into matter than antimatter. It's not enough to explain the universe, but it's a hint. So it's something that they were designed to really study specifically, whereas ALICE is really designed to be able to measure lots and lots and lots of tracks, which you get when you collide heavy ions together, like lead ions. And so they're trying to understand the quark-gluon plasma, the strong interactions and things like that. So there's a lot of complementarity there.
Right. Last question from me, because the questions from the audience are accumulating at a high pace, and I can see that we can basically skip the basics here. We have a bunch of physicists, I think, joining us online right now. So I'm not sure I'm going to even properly articulate the questions, but let's go ahead and try. So before we move there, you did say that there are plans to build even larger colliders. Now, you did cover that a little bit in the presentation, but still, I kind of missed the point here. Why are we building bigger ones? This 100-kilometer circumference collider.
Okay, well, let me tell you what we're doing right now. Actually, the LHC is down, not because of COVID,
right.
but because we were already planning an upgrade. So periodically, we do upgrades to our accelerator. Our goals, usually an upgrade, either you're going to get a little bit higher energy. Again, when you go to higher energy, you can find new particles potentially that are at a higher mass that you couldn't quite make before, or not at a high probability. Or you go to higher luminosity. And luminosity is really what we're pushing right now. That means more collisions per second. So you're focusing the beams, you're using different kinds of magnets or different algorithms, different ways to make the collisions. And that gives you much more data flying out there. And so you also have to upgrade your detectors to be able to handle this faster data rate. So it's because the technology now allows us to do this. So we upgrade and we fix that. And then you can measure really rare processes. There's some things that only happen once in a gazillion times. Mm-hmm. So you want 1,000 gazillion collisions so that you can find 1,000 of them. Gazillion doesn't really exist, but it just so you know. But that's the idea. Is something's really, really rare, you want to measure that, and you also want to measure things very precisely. The higher statistics you have, the more collisions you have, the more precise your measurement can be, and then you can try to find out where you deviate, where the standard model deviates from reality, because we know it deviates because there's 95% of the universe we can't explain yet. So we know what we have in the standard model is not enough. We need more. We know there's something else out there. We want to find out where our model is broken. Okay, so then we can move on. Now, So the luminosity, we will increase in luminosity. Then after several years of running, we will go down again for a long period of time, do some more serious upgrades, even more serious upgrades, and go to what's called high luminosity LHC. It'll be about 10 times the luminosity we were getting, which is a lot. And so we will work at high luminosity LHC for some time and get data from that. But in the meantime, new accelerators, you have to start planning really early on. You can't have a gap. We can't have a time where we're done with the LHC. Okay, now let's go build the next thing. Because then you lose all of your students. You lose everybody. You lose all the people who are working. They have to have data. They have to have things to work on. And so we have to time everything to try to get it ready. And we see the new technologies there. And we have big questions. So what we found now has led to these big questions. We want to produce lots and lots of Higgs bosons so we can measure it precisely. We know that. We sort of knew that even before the LHC, that if we found it, we want to do that. And we want to explore. We want to find out what else is out there. What are these things? What's dark matter? And what are, and all the other parameters of the standard model. There's a lot of parameters, a lot of stuff. It's not right? It's not the final thing. We know that because we have to put certain numbers into it to get our solutions. And there's got to be something more fundamental out there. So these questions of Og are still with us. We need to answer them. The way to do it, we know the technology that's needed. We think we can do it in an economically feasible manner, something which will, just like the LHC, spit out more, cause more gain in economy than it costs. The LHC has already paid for itself in its increase of the world economy.
Right. So because there is a question related here to the standard model, and if there is something outside the standard model. So we do know that there is something outside the standard model, and these big colliders are the way to find out what. Is that a correct statement?
It's a correct statement. I hope the big colliders will give us the answers. There's never a guarantee.
Of course, yeah.
You sail across an ocean, you don't know what you're going to run into. Well, now you do, because we mapped the whole planet. But you don't always know. We do know for sure that a tremendous amount of physics will come out. Just like I showed you all of these rows from the CMS exotic search, we will map things out and we will know our universe better. And in fact, and part of that goes into the planning. What will give us the best constraints possible? It doesn't sound sexy. It sounds better if I come up to you and say, hey, we've just found the Petco particle. Then you get excited, but all that other physics has to get done.
Right. All right. So we have a question from Faraz Baik, one of the few people who actually came out with their own name. So let's see the question. So does CERN have a long-term plan to identify dark matter particles at various energy levels and along the way rule out some contender particles? And we have here in brackets supersymmetry.
Yeah, that's still in the running. Supersymmetry, in a lot of the different like minimal supersymmetric models, there's a variety. Let me just step back a second. Supersymmetry is an idea. It's actually a framework. It's beyond being a theory. It's actually a theoretical framework, which attempts to actually simplify things in the end. To do so, it actually has to double the amount of particles. For every one of these sort of matter particles, it turns out there has to be a force particle. It's a kind of symmetry that's there. But that symmetry would help us to understand how these forces come together. Right now, they're sort of independent. Electromagnetism and the weak nuclear force come together, but they aren't really connected to the strong force yet. We don't see how we don't have a theory that really connects them to it, as well as gravity. Supersymmetry tries to explain all of that, and it's a really elegant model. Mathematically, it looks really, really nice, and it's certainly worth pursuing. Unfortunately, we haven't found any real evidence for it yet. Optimists, theorists who are optimists, will say that we've already found half the particles. We just have to find the other half, but that's optimism. So supersymmetry is something that's still being pursued. We're still putting strong limits on it, but it's still out there, and that's a possible explanation. The lightest, just like I said, the lightest particles that we know of are what we're made out of. The lightest supersymmetric particle would be the candidate for dark matter, because we so far haven't been able to measure these supersymmetric particles. They just don't interact with us very strongly. But the lightest one would be stable. Same thing goes there. So yeah, we're looking at that. We have general searches. We have many different searches in the LHC for dark matter. It's an interesting thing to look for. In general, you can look for it by looking for what you don't see. When you make collisions like this, if you look in this plane here and you add up the projection of all the tracks on that plane, they should add up to 0. That's conservation of momentum. Tells you that, and conservation of momentum holds. So if you see that there's nothing coming out a part of that detector, you add them all up and there's just some nothing missing, something's missing there. Then you measure that and you plot that, and we do that. And where our plots look like now is what you would expect from contributions from neutrinos. Neutrinos don't leave anything in a detector. But maybe we'll get lucky. Maybe out there we will see a bump and we will see something else that's contributing to it, and that would be a candidate for dark matter. There's a lot of other beautiful dark matter experiments going on outside of CERN as well. Down in gold mines, for example, or up in space. Even the AMS is actually a CERN experiment or associated experiment up there on the space station, and it's also looking for candidates of dark matter.
Right. Now, you did mention neutrinos, and we do have a question about them. Now, until recently, we believed that neutrinos do not have a mass, but modern research shows that it seems that they do. Can you tell us something more about the current state of neutrino research?
So yeah, the mass comes from the very fact that we see and we've measured that neutrinos can change from one type of neutrino to another. So in general, you have 3 kinds. They associate with each of the leptons. So there's electrons, muons, and taus. There's electron neutrinos, muon neutrinos, and tau neutrinos. And some great experiments. I think the one that really found conclusive evidence was Supakamiokan, which is located in Japan. They measured neutrinos coming from the sun. What they found, the sun should produce electron neutrinos. We know the interactions. We know what the sun is. It's a nuclear fusion experiment going on out there, and we measured that these neutrinos converted to muon neutrinos, and we can then do experiments. So Supakamiokan can measure also you can send a beam. We can send neutrinos through the ground. It's not a big deal. They go right through the ground. They don't interact. But during that time, some of those that come close to nuclei they can swap. And they can become, an electron can become a muon neutrino, or a muon neutrino can become a tau neutrino. And we can measure that. So we take neutrinos, and we do that actually at CERN as well. CERN shoots neutrinos through the Earth down to Italy, to Gran Sasso, where there's a huge detector. They're usually like enormous volumes of liquid with sensitive components all around it. And when a neutrino, if a gazillion neutrinos go through, there's a probability that a few of them will interact. And they interact with a nuclei, and then you can see the signature of that because those particles will hit the outside of the detector with the sensitive parts there. So these experiments have shown us that they can swap from one to the other. And in order for that to happen within the standard model, it means that they have mass. There'll be some great experiments coming up. The CERN is got something called Proto-DUNE, which is testing for a big experiment that will be built in the US called DUNE, that will take beams of neutrinos from Fermilab near Chicago and shoot them underground into a detector there.
Mm-hmm. Sounds really cool. All right, so we have a question from Charm Quark. Okay, so what is quantum gravity, and is CERN going to find gravitons? So what happened to the graviton?
I've never heard from a quark before. At least it's Charm I got to hear from.
Aren't we all made of those?
We're all made of it. Charm, well, only a few of us are made of charm, right? Petco, yeah. Charm, unfortunately, disappears very quickly. It transforms, and we end up with ups and downs.
Right.
So yeah, are we going to find? So the question was, we talked about this. Are we going to find gravitons?
Right. Yes.
It's something we've looked for. It's in our searches. It's possible that certain types of gravitons, excited states of gravitons, could decay. I think the signature is essentially a couple of photons that come out at high energy. As we look for resonances, high level resonances. There might be other searches that I'm just not aware of. followed everything on that. But I mean, at graviton, it's really interesting because it's something that we're kind of assuming exists, right? All of the forces forces, I should say, interactions are carried by some sort of boson. And we have these bosons on our table. So I mentioned that a photon is a good example. That is what gives the interactions for electromagnetic interactions. The weak forces are carried by the W and Z bosons, or Z, depends where you're from. Those cause the interactions that are the weak nuclear interactions. There's the gluon, which gives you the strong nuclear interactions. And it's assumed that gravity similarly has something called the graviton, which would be the boson, which carries that force or those interactions. And so we're looking for it, yes, but it's something which is not necessarily easy to find. We don't know.
Right. Okay, so we have one interesting question coming out from Facebook. Just give me a second. Where did it go? By the way, Eva, popped up in Facebook as well, and she says hi. So we also,
hey.
Yeah. So
hi, Eva.
So we have a question from Milena Georgieva. She's also a friend of ours. She's a very fine molecular biologist and a great science communicator as well. So she's making first a statement, and then she asks a question. So she says, as a molecular biologist, we assume the cells, particularly the nucleus, pretty much resemble the dark matter. And then the question is, do physicists believe that similar powers and particles could possibly influence genes, cells, and thus the cellular fate? So what do you think about that?
I'm not sure I understand. Could particles, wow.
That similar powers and particles could possibly influence genes.
I mean, okay, I mean, I'll say what I know, which I'm sure she knows this already.
Right.
The little bit that I know about interactions with genes, for example, it's been proposed that it's quite possible that cosmic rays. So cosmic rays are rays that go through us all the time. We have them passing. We have muons, for example, passing through our bodies. Several per second are going through us. Depends on your energy cutoff for that, but they pass through us all the time, and that's because there are high energy charged particles that hit our upper atmosphere of our planet, and when they hit, they cause an interaction. Often they form things like pions, which then decay or they transform into muons, and the muons then come down through us. That's in fact one of the reasons our field got started. Victor Hess measured these. He was actually trying to figure out if radiation he was measuring in his devices was caused by stuff in the ground. He was expecting measurements that as you go down, that the interactions would go up, and as you go up, they would go down. And in fact, he found the opposite. And he ended up riding up in these balloons that went way up, high up. He risked his life. He improved his instruments, and he found out that there were interactions up higher. You get more cosmic rays, more interactions as counters were going up. And so they're going through us all the time. It's quite possible that they play an important role in evolution, that high energy particles came down and hit our DNA and made changes. And those transformations came up with people like Petco, for example.
Yeah. What an accident.
Yeah, it was not an accident. So, and so these mutations in our genes could have been caused by high energy particles, and that could have been from cosmic rays or from other things. There are in our soil, there's various things which are radioactive. Uranium is one of them. Radon. There are things that are out there radioactive, but for the most part, there's very little that's going to really affect us unless there's a high quantity.
Right.
So I don't know. I mean, that they can affect. I'm sure I'm not answering her question, so she should contact me and we can talk over a virtual coffee sometime.
Oh, you'll have fun with her. She's fun. All right. Speaking of friends, we have one more friend of ours, Vladimir Nikolov, is asking a question. Vlado is one of the few people in the world who is doing paleo paintings of dinosaurs and general paintings of the paleo world. So shout out to Vlado. You can check out his things. He's an amazing artist. So Vladimir Nikolov is asking, what's the most probable hypothesis, given what we currently know, explaining why baryon matter and dark matter do not interact with each other. So do you understand this question?
Oh yeah, I understand that question, but I don't have an answer. I don't know why. And what's the most probable reason? I don't think we'll know that until we actually find out what dark matter is. Yeah, I would have to talk to, I know some experts, and if he contacts me after, I can try to point him to one as to why it doesn't interact with just normal matter, baryonic matter, as us, right? Protons, neutrons, and all that. But I hate to even try to speculate, because we don't have a clue what it is. Or even if it's we don't even know if it's a particle or not. I mean, that's most of the assumptions we have, is that there's a particle that's being produced. We don't know if it's massive. We don't know if it's not massive. Is it a WIMP? Is it a macho? It's all the names that we use, or acronyms. Or even if it is a particle. There's different ideas that it's something we don't understand in gravity itself or something like that.
Right.
Which doesn't seem to really pan out with most of the measurements. So there's something out there that's massive, most likely. But why it doesn't interact, I don't know. I hate to speculate.
That is very humble of you. That's what science does to people, right? Very good.
Yeah. We find out how much we don't know.
Exactly.
We find out we're insignificant and we don't know anything. There we go.
Yes. My dad used to say that it's a measure of maturity to understand how insignificant you are. So he's correct in this sense. So next question. So speaking about the Higgs field, you spoke about that a little bit. That the Higgs field is giving mass to the particles essentially. So the question is, are photons interacting with the Higgs field?
Photons don't directly interact, because photons are massless. So at least from the theory, and the theory seems to be panning out very, very well. You might say, but you guys told me that when you first found the Higgs boson, it was by it decaying to 2 photons. So what's up with that? They must interact. And the truth is, let me take a step back here and explain a little bit. Well, if we have the time, because I like to sort of explain this. Experimentalists, we look at what we know, what goes in. We're taking photons, and we know what comes out. We have these devices to measure what comes out. What we don't know is exactly what happens on the inside. Okay, that's where theorists live. They live inside. There's a little area there. In fact, we're told by Heisenberg, we'll never know. We're never going to get inside. There's a certain area that we will never get into. We're never really going to know exactly what happens here. That's where our field comes from, is trying to figure out what happens inside there, what's allowed to happen. We have these rules. You have the coffee cup full of rules on it. And so that gives you different things you can calculate. You can say, okay, I know that this particle can form this particle and can interact with or make these 2 particles, etc. So what is allowed to give us 2 photons is that you have a Higgs boson. The Higgs can then interact with other particles like a B quark or a top quark. We can measure how much. If you saw my plot, top was way up there at the top. Why? It's the most massive. The most massive particles are more massive because they interact more with the Higgs field. Okay? Now, what's going on in there, what we think, and it just works out with the calculations, so it's hard to believe it's wrong, is that the Higgs gets produced, and then in a sense it transforms into 2 tops, a top actually and an anti-top. Okay, you can think of it that way. You can actually, the diagrams don't care if that's a top that goes like this and gives out a Higgs. You can go backwards in time with the calculations. It's all the same thing. That vertex, that thing there has a value to it. The Higgs boson, and then top of it, and then those can then shoot out a photon and make another top quark. So you have this triangle of top quark. It's like a top quark that's going like this in a loop. And the photons are coming out of the vertices here, and the Higgs is going into a vertex here. That's allowed. That's on the coffee cup. That can happen. So then what we do is we simply calculate, okay, what's the probability of this happening? So you draw these diagrams that would allow it to happen. And you can then calculate with that equation, what is the probability of that happening? And we do this for all the combinations. So you could have just the Higgs doing that. It could also shoot out a top, which then goes in a loop and does this and that, and an elephant gets formed or whatever. You're allowed all these things on the coffee cup can happen. The thing is that each time you have a vertex, each time you have one of these little spots where particles meet, it adds a probability. Okay, and probabilities, when you multiply them by each other, probabilities is a number between 0 and 1. The more you multiply, the smaller probability gets. So you can end up with an infinite number of possibilities. There are, in fact, an infinite number of things that could have happened to get those two photons. But this was really key around the 70s. Yeah, I think it was around the 70s and 80s. These guys figured out that even though there's an infinite number of things going on there, the theory works because you can add up an infinite number of things. You can make an infinite sum. And as long as those things are decreasing in value each time, it comes out to a number and you can calculate it. So these guys, the brilliant people, came up with this thing that's called normalization, which allowed us to calculate. So we can calculate what is the probability of us producing the Higgs boson, which actually was also another loop, but I'm not going to go into that. Okay.
Right.
But then, and then what's the probability of it forming two photons? So in a sense, it indirectly interacted with the photons, but there is nothing on the coffee cup that allows a massless particle like a photon to directly interact with the Higgs boson, and we don't see it. We don't see that. Right. That would have changed the value we got out of it. If it could indirectly do it, we would see photons, right? More, higher probabilities, or change the probabilities. So far, the precision we have now tells us that they were right. What they predicted was right, and massless particles do not interact directly with the Higgs boson.
Right. All right.
Long answer to a short question.
Yes, but we love these answers. It's more than fine. We have an interesting question here. I'm going to get you back to the subject of dark energy. The question is it possible that dark matter, or at least dark energy, might be the result of a mistake in the standard model, and that their existence be denied in the future?
Oh yeah, they are a mistake. There's definitely a mistake. A shortcoming of the standard model. So I call it a mistake. I have a good friend who likes to tell me this when he teaches his physics classes, that, there's nothing wrong with flat Earth theory. Right. If you're building a house, right? Mm-hmm. Earth is flat. Well, I mean, it's got bumps in it and all, but in general, you don't care about the curvature of the planet at most levels. It only takes you doing precise calculations or leaving the planet and looking at it from outside, or noticing that its shadow on the moon is always round, which people did, thousands and thousands of years ago when they already knew it was round. That theory is fine for the devices you have that you're measuring with. When you look around here, I'm looking with my eyes, it's a little bumpy, but it's flat. Okay. Right. So, the standard model is fine. It's a good theory. It's incredible. The predictions it's making to decimal places are just outstanding. But we know ultimately there's something beyond it. We just know that because there's these things which aren't answered, like dark matter and dark energy. So they're going to take us beyond the standard model. In which direction, we have no idea. There'll be a whole new set of particles out there. Maybe there's something we don't understand in the interactions. It's our ignorance. I mean, it's just, I wish I could just, I don't know, freeze myself and come out in several generations online and find out what was, dark matter and dark energy, and hear people laugh about how we called it that. Because, I mean, this field is what, it's 100-something years old. It's not very old. We've come huge way in a short time. It won't take long until they finally come out with something and realize what it is. But it won't be in the standard model. It's just not in the standard model now. So I'm pretty sure it will be a mistake. Or a shortcoming, but I don't know what they are. Sorry.
Right. All right. So it seems like every talk that we have around physics, the question of string theory comes up. So I'm going to ask you a question around that. Do we have any significant progress in disproving or proving the string theory, or is that a long shot?
I think that just depends on the theorist you talk to. Right. If they are a string theorist, then yeah, we're making progress towards it. Mm-hmm. String theory, I can't even do justice to trying to explain string mm-hmm. theory. I mean, very roughly speaking, you can think of matter being made of strings. Each particle is a sort of an excitation of that string. I mean, already when I think of it, already it is a part of our field that any particle is a field, and any field is a particle. Okay, that's already something that's quantum field theory. That's deeply ingrained in what we're doing. Is how we can do these calculations is to know that. Okay, and that's already really complicated. It took me a year to come out with a simple animation to explain that the Higgs field, that the Higgs particle is an excitation of the Higgs field, you know, and that's just, it's really hard to comprehend for us simple people, also because of the dimensions we live in. String theories, I think, to me, it goes, you know, beyond that. It's something which could come if there's supersymmetry that can help to support string theory. I think I understand that. I could be wrong, but I think I understand that. But it's a very complex thing, and so I don't know. You know, people will say, "Oh, we've pretty much are done with supersymmetry. We've eliminated it because, you know, we've looked at all these different areas." Well, no, there's a lot of area out there. There's a lot of phase space, we call a lot of space where we can look for supersymmetry, and so I wouldn't count out something like string theory at all. But I don't know anymore. You need to get a theorist on sometime who can answer these questions.
Well, you're going to have to help us with that. You know, they're not.
There's some good ones. I can find you a good theorist.
All right. Sounds good. I'm going to follow up on that with you. We have a cool question here. So, does dark matter clump like the ordinary matter, and could there be dark matter planets or even beings?
Oh, that'd be cool. Dark matter being. I don't know about that, but that's an idea. It does clump. They map it out. That's the amazing thing. There's these sky surveys that are getting more and more precise. And there's going to be even better measurements coming out, not so distant future. I think in the coming decade or so. Beautiful devices, which what you look for is the lensing of stars. So imagine you have you know, dark matter somewhere, and you have, so something massive. There's something massive out there, but it's not sending any light to us. We don't see it. Light, just like, and it's a similar thing for a black hole. Okay, they're different. A black hole will interact with. You don't want to go near one of those. But light, we'll see light from a star that looks like it's there, but in fact it's really there because it curved around some bit of mass. So certainly there are clusters and clumps of dark matter out there. That's been mapped. There's a whole, you know, there's some images of it. If you look this up, right, you find this World Wide Web thing is useful. You can look for structure of the dark matter in the universe, and you'll see this sort of web-looking thing, which is somewhat of an artist's depiction, but it tries to show you the areas where there's more of it centered. I don't know if, you know, beyond that, I don't know that you can have dark matter stars, or there's a search for dark photons. So it would be something which interacts between dark matter and real matter. So I don't know, maybe there's a whole dark universe out there. They haven't come to see us. Yeah, maybe they just don't see us. Right? That must be light matter. We can't see it.
Right. All right, a couple of more questions. So one of them is pretty interesting. We know that you are producing antimatter in the LHC, right? So there's been a lot of speculation of what, you know, devious things you guys are doing out there. You know, you're trying to blow something up. So I don't know why the question is postulated this way, but it was submitted by our friend Nikola Kerekov. So the question is, how much will it take to blow up the Vatican? I have no idea why the Vatican in particular, but I guess there is something in there in this question.
Well, they watched Angels and Demons,
yes.
or read the book. Right. It was wonderful. Tom Hanks came here, and they shot film here. We were happy to have them do that. The Vatican wasn't so welcoming. They had to do it sort of clandestine over there. Right. So let's start with antimatter. Okay. Everybody, get your pens and pencils out. Are you ready for this?
Sure, I'm ready. I'm recording this session, so
yeah. What is antimatter? Antimatter is a really cool artifact, in fact, of the fact that there's a square in an equation. And Dirac noticed that you know, in fact, you have this equation which tells you, you know, E squared plus P squared plus M squared, and he came out with this and he said, well, look, what this all means is that there are two solutions. When your solution is a square, it means that if you take the square root of that, there's two solutions, there's a positive and a negative one. And he, being brilliant, Dirac, said, oh, well, that means maybe, you know, for something that we see that has a charge that's positive, it could have a charge that's negative. Antimatter is simply the exact same thing as matter, but with the opposite charge. Right. So an electron has something we call a positron. An anti-electron is a positron. It behaves exactly the same way as our proposal. And we've seen that. We measured that. You can even have protons and antiprotons. In fact, we've produced them in order to make an accelerator that did discoveries. We were able to produce antiprotons and to keep them around and have them collide, and that was very, very useful. You get a higher probability of having a collision if a proton and antiproton than if you have two protons, but it's not easy to do. So yes, we can produce it. Now the LHC, in the collisions, equal amounts of matter and antimatter get produced, but it disappears. Unlike in the movie where they're somehow magically siphoning off the antimatter. We can't. It, it disappears in the detector immediately. Right. Anti-muons might make it through, but then they disappear just like muons do. We can't capture that. But we do have dedicated experiments. We are very much interested in understanding and studying antimatter. And there's a great ones, the Alpha, Athena, Asakusa, I'm not sure I know all the names of them. We have something which is called the antimatter decelerator, not accelerators. We're taking antimatter. You take matter, you can take protons, for example, and hit a target, and you can produce antiprotons. And the antiprotons can then, using magnets, you can focus them and you can steer them, you can accelerate them or decelerate them in this case, into your detector, and then try to measure their properties. We've gone a little bit further than that. We've measured the properties of the antiproton. We've then taken and made anti-electrons, positrons, and got them to go into orbit on this to make anti-hydrogen. So we can study that. One of the experiments, I love this fact, it's a good fact. Carlsberg has a foundation, you know, Carlsberg beer, they have a foundation, and they have given funding to a good friend of mine, Jeff Hanks. He's the spokesperson from the Alpha experiment. And that's what, you know, is one of the experiments that is really trying to study this. We've taken, so beer is important. Again, that's the second time this theme has popped up. Is proving it. The anti-hydrogen, they've actually been able to probe it and look at its spectrum. So, you know, hydrogen, you can excite hydrogen, the electrons, and then look at the decay down to the ground states, and you can measure those spectra. So, of course, the question is, does anti-hydrogen do the same thing? Or do the positrons orbit differently or do something differently? And they've measured that, and they seem to be the same. It's a very interesting thing. One question that everybody has on their mind: does anti-hydrogen does it fall, or is it going to fall up? It's going to fall down or up? You know, does gravity work oppositely? Most of the theories expect that it's going to fall down, but because the only difference is really the charge. But you got to measure that. We're scientists; we have to measure that. So there is something that's coming up. They're going to actually be able to try to slow it down, put it into a beam, and look to see if it goes down or up. It's really amazing what they do with this. There's a lot of work on this. The amount, though, of antimatter that we produce is not enough to blow up anything. You know, it's people think of the energy that we make with these huge accelerators all the way around. They must be producing something that's terrifying and dangerous. When two protons collide in the LHC, which is the highest energy machine we have in the world, the amount of energy is this. That's it. It's nothing more than that. Now, what
very anticlimactic,
yeah, we don't cause earthquakes. We can't make a plane crash. We've been accused of everything. If you want to do a terrible exercise, I mean, I know why the question gets asked, and it's important to answer it. If you do a terrible exercise, is to go log out of YouTube, log yourself out, and then go and do a search for CERN. You'll find like 7 out of 10 is conspiracy theories. It's garbage. It's you know, these things which we're trying to outweigh.
Yeah.
And so there is a lot of crap out there. We can't do any of the stuff they say. We can't even conspire. Getting physicists conspire. If we lie, we're caught because we have so many people checking what we do, and our career is done. It's not like
well, that's essentially how you make a career in science, right? By disproving someone else's theory.
Sure. You disproving a theory is not that the theory was a lie. I mean, the theory needs to advance.
Yes.
And so, yeah, we're always attacking, criticizing each other, and we like that. We want that. It's a whole different world than politics. Let me say, that as far as the politics I've been seeing on TV, it's going to change. I know it's all going to change, but yeah, we have to be honest with our results. There's no way that we can conspire. And if you look, the amount. So actually, to finish the Vatican question, I should say that it is true in the movie. What was said is that if they got like a gram of antimatter and a gram of matter coming together would cause an enormous explosion. It would be stronger than Hiroshima, for example. It'd be devastating. To gather a gram of antimatter at the rate that we do it, and we lose it all the time. I mean, it gets shut down. I remember seeing Tom Hanks on a late night show. He was asked, he cried because he said, they destroy it at every Christmas time. When they turn off the accelerators, it gets destroyed. The amount is nothing compared to a gram. It would take us roughly 1 billion years to produce a gram of antimatter. And there's just probably much other ways to blow up places than that. Let's not blow up places, though.
Right. Let's even the Vatican. Let's
even the Vatican. I think that they were our funding source for a long time for science. Yes. So they're still good friends.
Right. Okay. A very practical question, and this is going to be our last question. So it's related to essentially scientific publishing. Right. So what we've seen is that we have a whole new, well, I don't know how new it is, but it's, I think it's a fairly new phenomenon of these, predatory journals, that are, what I'm talking about, this whole new pay per publish type of industry. So the question that we have submitted by our viewer is, how do we distinguish between those? I mean, how do we find out, what is the real thing?
What is what? It's not so easy, but I mean, there are certain, you can look at the ones that we publish in, for example. We're not going to choose to publish in something that's not peer reviewed properly. Open access, I think, is a great thing. It's something that CERN signed up for several years back, meaning that the journals that come out, everyone will have access to them. They don't have to pay because they can be quite expensive to get. So that's an important aspect of it. But there is a lot of work that has to go into getting it out. They do have to have these reviewers. They have to check the quality of it. So some of the organizations, for example, the American Physical Society, they help to produce one of the journals that we use. They had a lot of trouble simply because they need funding to be able to do their work. But they have found a way through people offering money and getting funding from other sources to continue on. So those journals such as from the American Physical Society, the European Physical Society, and these are legitimate journals. They're I don't know how to tell you which ones. I want to say that there are a lot of others that are just popping up, and I'm getting mail saying, hey, don't you want to peer review for our, don't you want to publish in ours? But I would suggest looking at the major experiments and looking at what they publish in gives you a good idea.
Right.
I don't like this. There's a lot of games in there I don't like. I don't like this whole rating system of who people get rated by how much their stuff is referenced in other journals, et cetera, et cetera. I don't think it's a good way for us to go necessarily.
Yeah, the science has its own problems that it has to deal with, obviously. So it's not a perfect endeavor, and thankfully there are ways to improve.
I love the idea that science is getting put out there. That's fine. That's good.
That's fine.
Publish.
And that's what we've set up to do here as well, Steven. So you've been very generous with your time. So I want to thank you very much for an awesome conversation. I'm very certain that the viewers also enjoyed that. We are receiving some excellent feedback on your talk as well as we speak. So again, it was a privilege of speaking with you once more, and I really do hope to see you live very soon.
Yes, I hope so too. I miss Sofia. It's a wonderful place. And so I look forward to working with you and your team. Petko, it was nice working with Nicola Demeter as well. And I miss Lubomir. Tell him he has to get back to work. All right.
Yes. Well, he's having dinner as we speak. So I crashed at his place, so yeah, I'm not at home. So it's a mess here as well, but I'm going to send his regards.
I missed the whole thing. And I also miss my good friends, the Silhouettes. Do you know them? These young musicians. It's a quartet there. I met them. We did something called the Music of Physics and Physics of Music.
Oh, I remember that. That was really cool. Yeah.
And they're great, and I miss seeing them. So I'm going to come back to town sometime.
Yeah, well, just fix the virus thing after you fix the public policy science, thing that we have going on here, and yeah, you're more than welcome to come back.
No problem.
Anyway, Steve, thanks very much again. I have a few words to share as well, but you're good to go. So I wish you a good evening, and we'll talk to you soon.
Okay, thank you. Take care, everybody.
Bye,
stay
Steve.
safe, stay healthy.
Yeah, we'll try. Take care, Steve.
Okay, bye.
Okay, for our foreign viewers, I'm going to switch to Bulgarian now, so you guys can tune out if you would prefer. Добре, окей, превключваме на български, сега няма да е особено лесно и това да се случи. Това събитие конкретно беше част от нашия месец на физиката. Август месец беше посветен на големите проекти в областта на физиката, на фундаментални въпроси. Разглеждахме произхода на материята в Вселената с свръхмощни ускорители, лазери, и сега се поговорихме малко за ЦЕРН. Говорихме си за анатомията на Вселената, и последното събитие, което ни предстои на 25 август, отново от тук, Рацио онлайн, и ще си говорим за енергията на бъдещето, за огромния проект ИТЕР. Очаквани фантастичен разговор за един от най-мащабните проекти, в които човечеството се е спускало, с огромни надежди, че това ще донесе на хората и на всички нас чиста и вероятно безплатна енергия, макар че едва ли. Нататък, какво имаме нататък, господа от апаратната, само да ми пуснете визиите. Така, следващото ни събитие, отново термоядрения синтез. Това е всъщност визията за събитието на ИТЕР. Както знаете, в самия формат Рацио онлайн ние правим няколко различни сегмента, така че там ще си говорим за човечество в бучка захар, отново интересни неща, ще си поговорим малко и за магнити, но основната ни тема отново ще е термоядрения синтез и ИТЕР. Иначе, ако искате да получавате повече научна информация, ето тук се обърках. Окей, на 9 септември, на тази иконична дата, ще си говорим за отрова. Тук няма някакви, ако щете, някакви семантични заигравки с конкретната дата, но ще правим нашето редовно събитие с музейко Science Night отрова, където ще разговаряме с 3 различни учени и експерти, с които ще си говорим за отровата в животинския свят и в човешкия свят. Така че от 17 часа в музейко заповядайте на нашето открито събитие. Едно от малкото такива, които си позволяваме да правим в тази ситуация. Но отново на 9 септември заповядайте на събитието отрова. Обещава да е фантастично. Може да проверите допълнителни детайли и в нашия уебсайт. Така, какво имаме нататък, господа? Благодарности, разбира се, на нашите патрони. В момента се нуждаем, не в момента, по принцип, разбира се, вашата подкрепа е безценна. Ние сме един немалък екип, така че благодарности на хората, които подкрепят популяризацията на науката чрез нас. За нас остава да се погрижим да го правим максимално добре, така че обещаваме ви, че ще се постараем да правим нещата все по-добре и по-добре. Като говорим за добре направени неща, изключително се гордеем с нашия подкаст. Може да слушате най-различни интервюта, както и разговори за науката, както с Никола Кереков, където разглеждаме седмичните новини, така и нашия формат Vox Nikili. Но в случай, че искате да разберете малко повече за ЦЕРН, може да видите и нещата, които сме правили преди това. Имаме разговор с Стивън от преди, мисля, че година и нещо, и разбира се неговото гостуване в самото Рацио, където отново говореше за големия адронен колайдер. Разговори ни с Чинтия Рао също, който е Science Communicator в ЦЕРН, също докосва темата за ЦЕРН, така че отново интересен разговор, проверете нашия подкаст. И нататък отново може да отидете и на нашия вебсайт, разбира се, където имаме най-различни неща. Просто проверете го. Там е цялото ни съдържание. Имаме ли още нещо, господа, което искаме да кажем на публиката? Вероятно не, така че за мен остават последните думи. Последните ми думи обикновено са свързани с няколко прости неща. Днес си говорихме за истината и за това как науката търси истината. Излишно е да казвам, че повечето неща, които виждаме в нашето съвремие, са и продукт на това, че ние не знаем първо как да боравим адекватно с информация, още повече пък да я синтезираме и създаваме по някакъв начин. Във всеки случай, струва ми се, че в сърцевината на всичките ни лични и социални проблеми, които виждаме, стои до някаква степен и неспособността ни да виждаме истината. Затова отново аз ви призовавам, следвайте доколкото е възможно научния метод и търсете истината във всяко едно нещо. На изпроводяк, разбира се, четете книги, подкрепяйте рацио, грижете се за себе си и се борете за демокрация. Това беше всичко от мен за тази вечер. Лека вечер, аз бях Петко Желязов и ще се чуем и видим следващия път.